So the goal today is primarily to work some example problems, but I want to review three things first. And that is, first of all, special functions. So just keep in mind the step function is shown. The step function is shown here. Remember, the step function is equal to 0 for t less than 0, and it's equal to whatever constant multiplies it. In this case, they're using k times u of t. So it jumps at t equals 0 from 0 to k. Technically, the function is not defined at t equals 0. It's defined for t less than 0 and t greater than 0. So we often will talk about 0 plus and 0 minus to represent the instant just before and the instant just after the step function moves. We can have a shifted step function. In that case, instead of u of t, it's u of, I don't know, this is an odd representation. I've never seen it written as a minus t before. Typically, it is written as t minus a. So I don't know what your textbook is doing. This is an unusual notation. So we'll just kind of put a line through that and remind you that this is k times u of t minus a. And I'm going to investigate that. I took this figure directly from your textbook, but that's an odd. Oh, okay, I see. This is if the discontinuity is to the left of 0, which is kind of irrelevant. So just disregard that equation. Remember that it's written u of t minus a. When we talk about the Laplace transform, we're always talking about the situation where t is greater than 0. Okay, and then finally, the impulse function. The impulse function technically is defined through the integral. But as we know, what it means is that del of t is equal to 0 everywhere except t equals 0. And theoretically, it has an undefined or infinite amplitude, but it can be weighted. So even though del of t at t equals 0 technically goes to infinity, this weighting function comes in because it represents an energy. So it represents the area under the curve, which can be relevant in certain aspects of EE, especially like in sampling. Also, the graphical representation of the impulse function, it looks like this with an arrow. The height is represented by this amplitude k. But once again, remembering that technically, since the impulse function has 0 width and an area of 1 or k if it's multiplied by k, then the height technically would have to be infinity, because 0 by times infinity is equal to 1. Okay, an important property of the impulse function is the sifting property, and we're going to work an example or two with this today. The sifting property basically says that if you have an impulse function, and it can be a shifted impulse function, and you place that under the integral sign with any function f of t, that then evaluates out to be the function evaluated at the point A. So those are the two kind of special functions. Lots of video lectures already made on these, but I wanted to have those up front because what I want to do with the examples today is work some examples that sort of integrate everything we looked at. Also, I want to remind you of the Laplace transform definition. Now, I believe now that all of you have had EE 3303 linear systems. So you should have seen the definition of the Laplace transform before, and you should see most of what I'm going to talk about today. So the goal today is just to work some example problems in a way as similar to what I would do in a live class as possible. The other thing I want to refer you to is I pulled up a table of Laplace transforms. So there is a question as to when you integrate to take the Laplace transform and when you use the table. This is just a random table that I pulled up. There's one in your book. There's one in most books. Mathematicians include a lot more transforms that we actually don't look at in electrical engineering, and this is kind of a mathematician's table. I'll draw your attention specifically here to the exponent. It's listed as a positive exponent, e to the AT. That would be exponential increase if A is a positive number, and that transforms to 1 over S minus A. So one of the things in electrical engineering is we don't have exponential growth, because if we did, we would blow up our circuit. So our systems, in order to be stable, are all characteristic exponential decay. So in that case, A would be negative, and it would be e to the minus AT. So A is not negative, but we write it e to the minus AT, and the transform would be 1 over S plus A. So that's the only thing I want to draw your attention to on that. Mostly what we wanted to look at on this transform table is the table of properties. So I'm going to keep this handy as we go through and find some example transforms. So pulling back up the Word file, and let's just get started. Change to a darker colored pencil or pen, and we'll just get started with some examples. So as written up here, the Laplace transform, the transform of f of t is going to take you from the time domain to the frequency, to the complex frequency domain. S is defined as a complex frequency. It is sigma plus j omega. And the transforming function, so to get the Laplace transform of any time domain function, we take the integral from 0 to infinity, and some textbooks will write this as 0 minus of f of t e to the minus st dt. So this function here, e to the minus st, we don't talk about this a whole lot, and I actually don't recommend ever doing this in problem solving, but it's basically e to a complex frequency times t. And so this first part, the sigma, allows you, using the Laplace transform, to represent transient effects. And the j omega allows you to represent frequency effects. So in many ways, it is a more broad and inclusive transform than a Fourier transform, because it's allowing you to model both steady state frequency effects as well as transient decay effects. And if you think about it, this e to the minus sigma t, e to the minus j omega t, represents almost every function that you would see in electrical engineering, with the exception of polynomials. So if you have exponential decay, which you get in like RC circuits, you would get that from sigma being non-zero. If you have some oscillation, which you would get in RLC circuits or AC circuits, then omega would be non-zero. So it really allows you to represent a broad amount of what's happening. It also encompasses ways to take into account initial conditions, which are important in transient circuits. If we have things like charged capacitors that we're switching over to inductors or switching over to an RL load, then it enables us to do that and to take into account those initial conditions. What it does not do is it does not allow us to model for anything less than t equals 0. So you're always, you've always got a system that is being switched on at 0. It can model transients for t greater than 0, but it cannot model transients for t less than 0, because we're using, by definition, the single-sided transform, which leads me to a comment about Laplace transform tables, and this is transform tables in general. When you have any transform table, the Laplace transform has, or when you go in the reverse direction, so you go from Laplace to time domain, the function f of t always has implied that it is f of t for t greater than 0 or greater than 0 plus. So the function only exists for t greater than 0. So for that reason, there's sort of an implied multiplication of f of t by u of t, meaning this function is only valid for t greater than 0. Otherwise, for example, if you write sine of at, that's a continuous function from negative infinity to infinity. So really, it's sine of at u of t. Some tables will express that explicitly, others will not. So you just have to be careful, but it is always understood in the single-sided Laplace transform. And we do not in electrical engineering utilize a double-sided Laplace transform. Okay, the other thing is that the Laplace transform is linear, meaning if you have two different functions and they're added together, the transform of the sum is the sum of the transforms. And then there are some other properties that will be useful. And so what I want to do today is I want to start off with talking about some situations on where you might want to integrate or not integrate on the Laplace transform. So when do we use the actual integral? So we use the integral when we can't find the transform on the table. So we use the integral when the transform can't be found on the table or in the tables. Do not make the effort to go and find a table with 775 Laplace transforms, because that's not the point. The point is when you get past these simple transform pairs, probably you need to look at another approach or a property or integrating directly instead of trying to search on the transform. So let's look at an example of that. Let's look at f of t is 3e to the minus 2t cosine of 4t del of t minus 2. Okay, so if you look this up, you'll see that you can usually find a table that has this first part, and you can find a table that has the impulse function, but you can't find a table with both. So the first thing I want to point out is that you absolutely cannot transform this one and transform this one and say that f of s is the product of the transforms. Multiplication is a nonlinear operation, and the Laplace transform is a linear operation. So you cannot perform a linear operation on a nonlinear operation. So you just mathematically can't do that. In fact, f of s, if you call this f1 of t and this f2 of t, if you wanted to take the transform separately, then f of s is actually going to be the convolution in the s domain of f1 and f2. So multiplication goes to convolution and convolution goes to multiplication. So you cannot, the product of the functions, the transform of a product is not the product of the transforms. So it's not like addition. So we have to look for another way. And in this case, one of the things that I reviewed briefly was the shifting property of the impulse function. So you may remember that the integral of sum f of t del of t minus a dt from minus infinity to infinity is equal to f of a. So a couple of comments about this. As long as a lies between the limits, this is true. This is true. So we technically don't have to go from negative infinity to infinity. We could go, as the Laplace transform goes, from 0 to infinity. So let's write the integral of what would be the Laplace transform of this function that I wrote above. So it's f of t, which is 3e to the minus 2t cosine 4t del of t minus 2. That's our function. And then we have to have our e to the minus st dt. And that's going to be our Laplace transform, which is written as capital F, a function of s. So now remember the shifting property. The shifting property says that basically in this case, a, the shift, is equal to 2. So all I have to do to evaluate this integral is I look at everything else that multiplies this impulse function. So this guy, and this guy, and I replace t with 2. So when I do that, I get 3e to the minus 4 cosine of 8 e to the minus 2s. And basically that's my answer. So the shifting property means if I have any function that's a product with an impulse function and I'm trying to take its Laplace transform, by all means, I want to integrate, not look up in the table, because you can't really find a function like this in the transform tables. So that's that. Reviewing. So I will say that on almost every exam that I've given in the time that I've taught, and I used to teach linear systems before we added circuits 2, and then I switched and I've taught circuits 2 really since its beginning, so probably 20 times. Every single test that I give over Laplace transforms, I include a problem like this. So it's easy points if you just learn how to do it. Okay, so that's that. So the next thing I want to look at is I want to look at some interesting applications of the properties of transforms. So let's come in and let's look at a function. Maybe it looks like this. And that's supposed to be rectangular. I know it's kind of trapezoidal, but it's supposed to be a rectangle. Okay, and let's give this a magnitude of 2, and it's a magnitude of -2, and this is t, so this is my f of t. So you have a couple of options here. One is that you could use the integral. So the integral would be basically you would say f of s is the integral from 0 to infinity of f of t dt e to the minus st dt, and your f of t would split into a non-zero function excuse me, equal to 2 between 1 and 2, and a non-zero function equal to -2 between 3 and 4. So I'm going to split this integral because most of it's going to be 0 into 1 to 2 of 2 e to the minus st dt plus the integral from 3 to 4 of -2 e to the minus st dt. And then I could do that integration and get a result. The other option is I can use the step function, and so that's what I'm actually going to work out because I want to review the step function. So I can use the step function and then use the table for the transform of a time-shifted step function. So let's look at how we would express f of t in terms of the step function. So the first thing I have is the function's going from 0 to 2. So it's going to be 2 u of t, and sorry, let me time shift that, u of t minus 1. So that represents this leading edge right here. And that's going to turn the signal on, and I'll get an output of 2 until I get to t equal 2, and then at t equal 2 I go back to 0. So the way to accommodate that is to then come in and subtract a time shifted step function that occurs at 2. So this one turns it on, and this one brings in a negative, and the net sum of that is that. Okay. And so then I also have the next pulse, which can also be represented by step functions. So I can then add, and because it's negative, I'm going to go ahead and subtract. The first leading edge occurs at t equal 3, and then it returns at t equal 4. So that second pulse would be illustrated by this expression. Okay, so now what I basically have is I have a sum of step functions, time-shifted step functions. So we could multiply that out. 2u of t minus 1 minus 2u of t minus 2 minus 2u of t minus 3 plus 2u of t minus 4. And so if you look up the Laplace transform of the step function, u of t, it's 1 over s. And then if you look up the property of e to the minus st f of t, find that that goes to f of s plus a. And I am sorry, because of the way I'm doing the screen recording, if you've joined and you have questions, I'm currently not seeing that. So I would ask first that unless you're asking a question, you please mute your mic because I do have some background noise that's coming through. And secondly, if you do have a question, just unmute your mic and for the moment interrupt me, because unfortunately I can't see both. Since I'm on the tablet, I can't see both the Zoom and my screen. So please feel free to interrupt if you have a question. Okay, so back to this, we're applying from the table, and I'm sorry. So what I was talking about is I was talking about properties. So first there's the property of multiplication of e to the st. The other property is there's f of t minus a, and I'm sorry, let me write a there, sorry. And this is the time shift property. So the time shift property tells us that if we have a time shift, we basically add an e to the minus as f of s. And both of these are important, whether we have multiplication by an exponent in the time domain or a time shift that ends up being multiplication by an exponent in the frequency domain. So the bottom line then is if you have the Laplace transform of u of t minus a, that goes to e to the minus as over s. Okay, so we'll go one at a time. So taking the first term, we have 2u of t minus 1. So a is 1. So we'll have 2 e to the minus s over s. The second term, we have minus 2 e to the minus 2s over s. The third term, we have minus 2 e to the minus 3s over s. And the fourth term, 2e to the minus 4s over s. And other than putting all of these with the common denominator of s, you can 2 over s, you can't really simplify beyond that. So you could simplify bringing in your 2 over s, e to the minus s, e to the minus 2s, e to the minus 3s, e to the minus 4s. Okay. So that is the property. Now let's go back and look at that on the table. It has a clear expression of that property. Here we go, right here. And I'm sorry, I can't mark on this. The pencil won't work. But if you look at this property called delay, okay, we refer to that in EE as a time shift property. So if you look at the property called delay, then that basically, this is the property that I just used, okay? And your book has a couple of pretty good tables. They call the properties of transforms, they call that, what do they call it? They have a weird name, operational transforms. Your textbook is the only book that I've ever seen use that term, but it's a fine term. It's just, I mean, that's what they call it. So when you see operational transforms, that just means transform property. Okay, let me go to the Zoom screen and just see if I had any people present who had any questions. And I'm not even sure, to be honest. Let me look at the chat. What is the exponent on E, and will we have this chart on exams? Not this chart. You'll have the chart out of your book. So there's 2 tables in your book. There's actually 3 tables on this material, and you'll have. You already answered the first question. Okay, got it. Okay, so let's go back and continue doing off the top of my head here. That's what I do when I teach live, is I just kind of walk into the classroom and make up some examples. So let me think. What do I want to illustrate next? Actually, while I'm thinking about that, let me ask you guys, if you have watched the videos, if you have any questions on anything. Well, I'm kind of making up another problem. Okay, not hearing anything. So we will go with this problem right here. So this is kind of an interesting one because notice the function doesn't turn on at t equals 0. It actually turns on at t equal 1. So we're going to use the time shift property that we did in the previous problem. But in order to use that property, everything in the function has to be time shifted by the same amount. So what I have to do is I have to go in and I have to do a little bit of algebraic manipulation in order to get everybody looking like t minus 1. So let's work on that. And what I can't do is u of t minus 1 is really more of a definition than a function. So I can't, all that does is it tells me the function turns on at t equal 1. So I can't change u of t minus 1. That's kind of fixed. So I have to work on the t and the exponent. So first realize that I can always subtract and add a 1. And I haven't really changed anything. So I both added and subtracted. And then remember that e to the ab is e to the a, sorry, e to the a plus b is e to the a times e to the b. So if I let a be minus 2 of t minus 1, and I let b be minus 2, then I can split this exponent into two parts. So basically it's going to be 3e to the minus 2t minus 1 e to the minus 2 u of t minus 1. Okay, and so this second term is just a constant, it's a number. So I'll just leave it as e to the minus 2 rather than plug it in. This term is my time shifted function. So let's pull out the 3e to the minus 2. And I have e to the minus 2, t minus 1, u, t minus 1. Okay, so now let's go to our table. And if we look at our table, so e to the minus 2t is going to go to 1 over s plus a. Go back. Okay, so if I had e to the minus 2t, that would transform to 1 over s plus a. But I don't have that because what I have is this time shift. So remember what the time shift does in the time domain. If you have a shift, that corresponds to multiplication by an exponent in the frequency domain. So pull out the constant 3e to the minus 2, just the number. And then if we were to transform that, if there were no time shift, it would be 1 over s plus, and a is 2. But then the time shift adds this e to the minus s. Why is it s? Because this is 1. So it's actually e to the minus 1s. So I get 3e to the minus 2, e to the minus s over s plus 2. And simplifying further if I want to, what is going on here? Somehow my Word file is going nuts. So I could simplify a little bit further. 3e to the minus s plus 2 over s plus 2. Okay. So that's that one. So that had a time shift, but I had to do some manipulation in order to get it to be okay. So let's look at another example. Let's see, let's let f of t be cosine of 2 pi t u of t minus 2. Okay. So let's work with that one. This one is kind of a trick. So what you have to realize is that the cosine of 2 pi times t minus 2 is the cosine of 2 pi t minus 4 pi. And because this is an integer multiple of 2 pi, that's just equal to the cosine of 2 pi t. So easy then for me to just make a substitution because they're equivalent and say that there's no change in the function for me to go ahead and make that t minus 2. Okay, and then when I do that, we go back to our table of transforms. And I always, at the beginning of the semester, when I do this for the first time, have to, pretty close to having it committed to memory, but not always 100%. So you can look at the table and see that the transform of the cosine of AT is s over s squared plus a squared. So if I did not have the time shift, this would be s over s squared plus 2 pi squared. And now what the time shift does is it adds an e to the minus 2s in the numerator. So that's my f of s. Okay, so let's extend that a little bit. And let's look at another function, f of t. What do I want to do on this one? Let's do t. Let's do tu of t minus 2. Okay. So this is a time shifted, it's a time shifted step, but the function itself is not time shifted. So this is another time when I'm going to have to do some algebraic manipulation in order to use the property of the time shift. So f of t is, so let's go ahead and do our minus 2 plus 2 thing. And then let's distribute what we're multiplying across the step function by splitting it up into the t minus 2 part and the 2 part. Okay, and so then the first one is tu of t, time shifted. So the transform of t is 1 over s squared. So I'll just write that down as 1 over s squared. And then the time shift is going to give me an e to the minus 2s. And then the transform of 2 is the transform of the time shifted step function. So that'll be 2e to the minus 2s over s. I don't have a math error there. Maybe not. Okay, so that is just then if we found a common denominator, which you do not have to. I actually, on an exam, prefer to see it in this form because it's way easier to grade. If you start to simplify too much and you make algebraic errors in your simplification, then it gets hard for me to track down, was it a math error or was it a conceptual error? So there's that. So let's pause briefly before I do anything else and see if there are any questions. And I think I only have actually a couple of people here. So you have the opportunity for your undivided attention. Okay, so the problems that I'm working out here are very similar to problems that I would put on an exam. The ones that I'll assign. So I'll assign some recommended homework problems, but then I'll also assign a kind of a MATLAB thing. So we're moving to more MATLAB as opposed to multisim from here on out for most of the course of the remaining semester. So that will be kind of the project this time, is just to model some stuff on MATLAB, which I plan to talk about on Friday, which will be done through Collaborate because it's strictly a MATLAB demonstration. Okay, so so I think that is about all that I really want to illustrate on the transform. I can do one more. Let's do one more. Let's take that previous function t and let's add a couple of things, because there are times when you have multiple different ways that you can approach a problem. So let me repeat, what you don't want to do is you don't want to take the transform of t, the transform of e to the minus 3t, and the transform of t minus 1, u of t minus 1, and multiply them all together, because that won't work. That's not mathematically allowed. So instead, what we have to do is look at some of the properties and how they might apply. So the first thing that we want to do is we want to be sure everybody has the same time shift. Sorry. So we want to change that first one to t minus 1 plus 1. And I'm going to mess with the 3t in a moment. I'm going to do this one first. So that would give me t minus 1 e to the minus 3t u of t minus 1 plus 1 e to the minus 3t u of t minus 1. Okay, so just took this and split it into two parts, this one and this one. All right, and now let me mess with the 3t part. So I have t minus 1 e to the minus 3 t minus 1 plus 1. And yes, you can combine some of these steps. I'm just trying to be very detailed, since some of you shouldn't be seeing this for the first time, but if you are, so that you can follow exactly step by step what we were doing. Okay, so then let me split up the exponent. So I'm going to pull out the e to the minus 3. So I'll have e to the minus 3 t minus 1 e to the minus 3 t minus 1 u of t minus 1 plus e to the minus 3 e to the minus 3 t minus 1 u of t minus 1. So for now, humor me, and we'll pull out the common term of e to the minus 3, and we're going to work on the transform of each of these. So we know that the transform of t is 1 over s squared. And we know that when it's time shifted, that we add that e to the minus s over s squared. So this is the time shift property. Okay, and then we also know from the previous thing I wrote down is there is this property of duality, that when we have multiplication of a function by e to the minus at, that shifts the Laplace variable. So if I now have and note that since everything is shifted, they all have to be shifted. So it can't be just an e to the minus 3t. It's got to be an e to the minus 3 t minus 1. That's why we went to all the trouble of changing all the time shift to be the same. So if I now multiply this by e to the minus 3 t minus 1 t minus 1, u of t minus 1. What that's going to do is everywhere I have an s, it's going to move it to an s plus a. And my a is 3. Okay, so all of the s's go to s plus a. So that'll be minus s plus 3 over s plus 3 squared. Now, would it have worked if we had gone in the other direction and we had taken care of the e to the minus 3 term first and then taken care of the time shift property? So in other words, if we'd done these 2 steps in reverse order, and the answer is yes, it would have worked just fine. So sometimes this is a point of confusion. Do you do the time shift property first? Do you do the multiplication by the exponential first? Do you do a derivative first in the event that you have a derivative? Sometimes this can be a point of confusion. So it actually does not matter as long as you're consistent and incorporate everything. So then doing both terms, this is kind of the same, except it doesn't have a t in there. So let me write that down and then I'll address your question. So the first term gives me the e to the minus s plus 3 over s plus 3 quantity squared, and the second term will just give me an e to the minus s plus 3 over s plus 3 not squared, and then both of them have this e to the minus 3 multiplier that I'll now add back in. So there's your Laplace transform. So once again, fairly straightforward, not a lot of mathematics, just the manipulative trick to be able to convert the time shift and make it common to every term in the equation. So really, as far as the Laplace transform goes, that's about as difficult as the question will get. Okay, so that's really all I wanted to go over today. We'll really keep our fingers crossed and hope this video actually is uploading to Zoom. And as soon as it does, I'll post a link on Blackboard. Before we close, are there any questions about this lecture material? Okay, well, thank you, those of you who joined me, for participating in this little experiment. And we will keep our fingers crossed that everything's safe and that this all works. Thank you.